Hello, everybody, and welcome to the virtual seminar series on Bayesian decision-making and uncertainty. We're super excited to have everybody here. Thanks for joining us. I'm Alex Terenin. I'm based at Cornell. I'm one of the organizers who's going to be hosting today. And I would like to thank my fellow organizers, Renato Berlingeri, Z Wang, and Natalie Mouse for their work in helping to put the series together. Thank you all so much for that. And before we get started, I'm just going to make a small amount of organizational announcements. First up, we've still got two more speakers lined up for the coming season. And you should check that out on our website, which is gp-seminar-series.github.io. So yeah, check that out. You can join the seminars via Zoom as long as you register for the Google group, which will mean that you get emails with the links, or you can always join us on YouTube, which doesn't require any kind of registration. Seminars always take place at 1600 UTC, which is Universal Time. And if you're joining us via Zoom, then you can ask questions by typing them into the chat, and the speaker can either pause and answer questions during the talk, or they can hold the questions to the end, depending on their preference. And with all of this said, it's my great pleasure to introduce Yingzhen Li, who is with Imperial College London and will give today's seminar. Yingzhen, the floor is yours.
Okay, hi, thank you for introduction. So let me share my screen. Okay, can you confirm you can see the screen?
Confirming.
Okay, cool. Okay, yeah, thanks the organizer for inviting me to give this seminar. So I think this is actually a very interesting seminar, and I'm very happy to talk with you basically our past and current research on the Gaussian process. So I have to say that probably this is like the two papers that I mainly publish with Gaussian process. My main interest is actually broader in less probability machine learning, but I hope that basically this talk will be interesting for this audience. So this work is done by my amazing PhD student, Wenlong Chen. So he led both of the works, but also the second work that I will talk about will also feature other PhD student Naoki Kirihara and also Harrison Zhu. Okay, so, well, essentially, I don't think I need to explain this slide, but what's happening right now in the crazy AI world is a lot of foundation models has been trained on a different kind of modalities like text, images, and also scientific domains like this, protein folding and also material design. Okay, one interesting thing to notice here is that the innovation in terms of neural network architectures are still going on, but at least at the moment, it has been settled down to basically two major themes. One is these transformers, and another is recurrent neural networks, at least in terms of processing the sequences. So there has been innovation in terms of how to implement or improve these models, and many of these implementations also involve some argument about linearizing transformers or making this linear version of recurrent neural networks. Okay, so lots of great things happening in the generative AI world. Okay, but apart from basically very nice performance in terms of generating the next token or predicting this protein structure or generating nice images, right? So when we actually apply these foundation models to domains that have very high security or safety standard, for example, like healthcare or like manufacturing or policy decision, then apart from prediction, you will also think about how reliable or how robust these large language models are, especially when they are trying to support these decision-making tasks. If you ask basically like doctors or like managers in factories or like policymakers in government about their hope or their wish for LN deployment, then they will ask whether the decision recommendation from the LMs come with a convincing explanation, or it actually follows some kind of causally meaningful reasoning process. And there might be some other factors that these people are also looking for example, like analyzing the risk of the predicted outcome, and also whether we can provide uncertainty estimates for the output from these foundation models. Okay, so we are going to talk about uncertainty estimate today. So, well, there are a lot of different paradigms in terms of uncertainty quantification, like frequencies and Bayesian methods and others. So in this talk, we are going to focus on Bayesian methods, where I'm just showing you the very basic idea about Bayesian inference. So essentially, Bayesian inference features this idea of updating the prior beliefs based on the data to get the posterior belief. Okay, right? So you will typically build up a prior distribution over the latent variable or over the unknown parameters that interest you. And then based on the collected data, then you update the prior of your variable W of interest to the posterior of W given data. Okay, here just to also say that this marginal distribution P data represents model evidence that people can use that to select a good model to perform. Okay, so now let's think about how we can apply this Bayesian idea to the world of deep learning or transformers. Okay, so basically around 1990s, right? So David McKay already specified some ideas about how to apply Bayesian ideas to the neural network weights and build this Laplace approximation to Bayesian neural network posterior. So around 10 years ago, right, this research field called Bayesian deep learning has surged as like an interesting research domain where people invented various different ways to train Bayesian neural networks. Bayesian neural networks are those networks with priors on weights, at least if you define it that way. And including myself, people have been trying to develop proximate inference algorithms to efficiently train Bayesian neural networks. Okay, so the research was okay in terms of progressing until the ChatGPT moment, where you start to see these gigantic neural networks like transformers, right? So right now, if you use ChatGPT or you use, let's say, Gemini, right, then the model size behind this the language model used by these APIs are probably like trillions of parameters. Okay, that's huge. So to my knowledge, right? So right now, the biggest Bayesian neural network that has been trained or at least been reported in the literature comes from this 2022 paper by Dustin Tran and colleagues at Google. So they really tried to train this, transformer-based vision model and language model using this method called deep ensemble as an approximate Bayesian inference method, and then evaluate its performance on various interesting, robust prediction and OD detection tasks. Okay, on various data sets. Okay, so they've got pretty good results, and actually show that there is this good potential for Bayesian neural networks to perform very well. Okay, on various tasks if you manage to scale it up. But the major challenge here is how do we actually scale up these things, right? So remember I said that you already have billions or even trillions of parameters of the weights in the language models. And many of the Bayesian neural network methods in the weight space require Monte Carlo samples or ensembling, which will even double the amount of parameters you're going to have, and also make the runtime in prediction time slower. Okay, so this major computational challenge is not going to be solved anytime soon, very unfortunately. Well, I mean, so Bayesian deep learning researchers, they are not just stopping there and then say we give up, right? And in fact, there are quite a lot of research right now that tries to apply these Bayesian methods in terms of fine-tuning for the language model. But that is not the topic today. Okay, instead, we are going to talk about something that views this kind of Bayesian deep learning paradigm, but in function space. Okay, So just to say that if you actually have a distribution over the neural network weights, right, then because one neural network weight parameterize one function, then random weights actually also gives you random functions. So this basically says, okay, so if you actually have a distribution over the weights, let's say prior or posterior distribution, then you will also have a prior or posterior distribution over the underlying functions represented by this neural network architecture. Another thing just to say here is actually in Bayesian deep learning, people care less about the weight distribution because we actually don't know what is the scientific meaning of the weights in a neural network. Instead, we care more about this predictive uncertainty. For example, in your regression problem, you might care about what is the predictive mean and the variance from your Bayesian neural network. Okay, so this kind of predictive mean variance or other moments for the predictive distribution actually quantifies the function space behavior of your Bayesian neural network. So this basically says, we only care about function space behavior of Bayesian neural networks anyway. Is there any way that we can, directly put functional priors or do some function space inference for Bayesian neural networks? So for sure, people have tried that, but that is actually not very easy. Okay. Instead, facing the difficulty of this function space prior for Bayesian neural networks, people look at some other alternative solutions, and one very natural alternative solution in terms of putting function space prior and also do this function space posterior update is Gaussian process. Okay, so I guess this audience of the seminar actually knows quite well in terms of Gaussian process, but just to give a very quick introduction, the key component of a Gaussian process prior is essentially the mean function M and also the covariance function or kernel function K. So you need to specify these two things in order to specify a Gaussian process prior. Okay, so here I just visualize to you how would this function space prior look like if you, I think this is a RBF kernel, right? So you have some interesting and diverse functions sampled from the prior, and once you observe some data which is shown in these black dots, then you can actually update your prior beliefs into the posterior belief of your functions. So definitely you can see that the uncertainty has been reduced. You can also just plot the mean function and the covariance function for this posterior GP. Okay, so GPs are actually very nice, and especially in regression problems, you do have analytic updates for the posterior. But again, the challenge of Gaussian process stems from its requirement for inverting this KXX matrix for the posterior computation. So this has n cubed cost, where n is the number of data points you have. Okay, so in order to address this scalability challenge, people have tried to develop Sparse GP methods, okay, trying to remove this cubic cost. So one kind of major class of this approximation approach is called Sparse GP, or if you combine with version inference methods, it's called Sparse versional Gaussian process. So the idea is the following. Okay, instead of inverting the big matrix, we will first introduce a set of inducing variables. Here we call it U of Z. Okay, so in this particular case, Z is like the inputs for these inducing variables. It lies in the same space as your data input X. Okay, so if you have these inducing variables, you can start from an augmented prior, which includes both the function values evaluated at your data locations, as well as these U variables evaluated at the Z locations. Okay. But then for these posterior updates, right? So we are going to basically construct this interesting posterior where you're only going to change the belief or update the belief for the inducing variables, but then keep the conditional distribution of your function f given you the same as the prior one. Okay? So why we are doing this? Well, if you actually use a big M number of inducing point and make sure that big M is smaller than, well, this is small n, sorry, then essentially you can reduce the computation cost of the posterior inference from n cube to mm squared plus m cube, where, m is much smaller than n. Okay, so this is the runtime cost, and then also the memory cost can be reduced to m squared. And here, people typically tune the variational parameters, basically the mean, and the covariance matrix of this QU distribution by optimizing the elbow. Okay, so here is a GIF visualization of what's happening. So here we show the training data point in blue crosses, and then we are just showing you how these GP feeds goes on. You can basically see that the red dot represent the inducing points, okay? And during the optimization, these inducing points moves, right? And then after optimization, it actually gives a pretty good feeds to the data, okay? And also provide uncertainty estimates. Okay, so people are actually very happy with Sparse GP as a way to approximate this GP posterior, and people have actually tried to spend time to generalize this idea and introduce this to the deep learning world. So notable efforts within this field include deep kernel learning, which basically says my kernel function now depends on a neural network, okay, instead of something simple like RBF kernel. So some other things like last layer GP basically says I'm going to pre-train a neural network and then I'm going to linearize it. Okay, use this linearization of the pre-trained neural networks plus Laplace approximation to construct this kind of GP formulation. So you can also actually stack up GPs. So this is the effort of deep GPs. At the end of the day, deep GPs, the function prior and posterior is no longer Gaussian. The hope is that just similar to stacking neural network layers in the deep learning paradigm, stacking GP layers into deep GP hopefully can give us some kind of flexible representation learning. Well, they are all very good promises. Unfortunately, they haven't sort of like show super promising applications, at least in the deep learning world. Okay, so we discussed essentially what's happening within the deep learning, well, Bayesian deep learning and also Gaussian process world, right? So both directions tries to push the Bayesian paradigm into deep learning and also try to make a successful strategy, but none of them were very successful. Okay, so we said that we want to look at the function space behavior. We still want to use GPs, but we also want to make it beneficial, okay, in the deep learning applications. So basically within this talk, I'm going to talk about two pieces of work from our lab, okay, answering two questions. So the first question is can GPs inspire ideas for uncertainty quantification in this Bayesian deep learning paradigm? So the second question will be, actually, can we also bring in the state-of-the-art deep learning architectures like transformers or recurrent neural networks to inspire new advances in scalable GPs? So I'm going to describe the technical work from now on. Okay, so the first one is done basically, well, almost purely by my PhD student, Wenong Chen. So this was published 2 years ago at iClear 2023, where the idea here is to show you how to introduce these, sparse Gaussian process ideas into attention and then make this kind of transform architecture like a Bayesian. Okay. So here I just want to show you the sparse GP equation again, but with one small twist. Okay, so we said that we only need to fit the Q distribution over the U variables, where we are going to parameterize the mean and the covariance matrix if you are doing conventional sparse GP. Okay. So once you've got that, then you can get the analytic solution for the mean and the covariance function for this QF. Okay, so it reads like this. So one small reparameterization that we're going to do from now on is that notice that this MZ is your free parameter, right? You can actually combine this KZZ inverse with MZ to get this another form of free parameter A, and we are going to optimize A instead of MZ. Okay, so some people in the Sparse GP will also use this trick. Okay, so from now on, the Sparse GP variation parameters are this A vector and also the covariance matrix S. Okay, so I'm going to review a bit about attention. Okay, this is also fairly well known, especially if you are coming from the deep learning world. The key idea here is you have this input of query, key, and value vectors, where you are going to use these queries and keys to construct a attention matrix, or in other words, a similarity matrix, and use this attention matrix to retrieve the corresponding values in your vector, in your value vector according to the similarity between the queries and keys. Okay. So people use softmax attention in transformers, but this attention can be generalized to something called kernel attention, which people have also tried in the NLP world. Okay, so you can pretty much see that this activation function on QK transpose can be replaced by a kernel matrix that acts over the query and the key vectors. Okay, so I hope that you already noticed this similarity between the kernel attention formulation and also the posterior mean of sparse variational GP if you use my new parameterization of the Q distribution. Okay, just to make it super clear. So this kernel attention is equivalent to the posterior mean of a sparse variational Gaussian process if you view the queries Q as the X, basically your data input, the keys K as the inducing point locations Z, and also the values V as these variational parameters A. Okay. So this basically means that, with the transformer architecture, we pretty much already have the posterior mean of a deep GP constructed. Okay, then if we want to quantify uncertainty and want to leverage the GP idea, then a natural thought is to incorporate the covariance matrix from a sparse variational Gaussian process. And this is what we did 2 years ago. Okay, so specifically, so this is a visualization of what we've done. Okay, so if you only look at basically the parts of QKV input and also compute the M pulse, then this is essentially the same as kernel attention. Okay, so we just complete the variance part by plugging in the covariance equations from the sparse GPs. Okay, so this is a pictorial visualization. Okay, so this sounds simple enough, but there is one catch. Okay, so actually in transformers, people implement that via self-attention. This basically says your QKV vectors, they are not independent. They come from a projection of your input sequence via these projection matrices W, QK or something like that. Okay. So this basically means you are quantifying this posterior mean over the sequence input S. Okay. And it says, if you also want to quantify the variance, right, then you may want to do the same by somehow projecting your input sequence to, let's say, some covariance parameter of your Q U distribution. Okay, so this becomes challenging because if you just naively project your input sequence as with length t to a covariance matrix parameter, then you will need to build a projection matrix with output size t squared. Wow, this is not very friendly. So nowadays for these transformers language models, the sequence length can be thousands or even let's say tens of thousands. Okay, not very good. So instead, we tried something from this decoupled GP idea by saying that, okay, instead of having basically, shared mean and variance using the same inducing point variable, we are going to have two sets of inducing variables, one set for the mean and another set for the covariance. So the details does not matter here. You can check the Chen and Booth papers if you are really interested. But by doing so, we are going to have a global set of inducing points only for the variance. And you can actually control the number of global inducing points. We denote it as mg. So this means instead of having t square memory, in addition, and also a t cube time, right, for basically these inverting matrices, we can now still achieve basically this, mg cube matrix inversion time, and also only maintain mg square more parameters. So this is our scalable solution to introduce the covariance to each of the layers. Okay, so I'm going to show you some experiment results, but to understand the experiment results, we need to talk about this, calibration concept, right? So, for example, like in classification problems, like image classification, a classifier is calibrated if the following holds. So if you have a set of test inputs where you can say this test input overall, a set of test inputs overall, I predict my answer with, let's say, confidence 0.8, then on average over this set of inputs, the accuracy should be 80%. Okay? So this is the concept of marginal calibration, and we can use this concept to construct the calibration metrics like expected calibration error, which you can think about is as the area of these red boxes in these calibration plots. We can definitely also compute the maximum calibration error, which is basically the maximum height of this red box calibration gap. Okay, so we test out our approach with various different methods, especially those weight space Bayesian neural network methods applied to transformers. So long story short, our approach actually achieves the best performance in terms of getting the best trade-off between, let's say, maintaining good accuracy versus having lower ECE. So you might see that mean field variation inference on transformer weights, right? They perform actually quite good in terms of calibration, right? But they have a poor performance in terms of accuracy. Okay. Also, we've tried to, do the ensemble version of this method, what we call SGPA. So which basically means instead of having only one transformer, we're going to ensemble various transformers together. And you can basically see that comparing to just simply doing deep ensembles, our approach also improves the performance. So we can also talk about some other tasks. For example, so Bayesian neural networks has also been tested in terms of its robust prediction on all the data points. Okay, in this case, those all the data points comes from this noisy perturbation of the clean images. So we test out these again on this, CIFAR 10 and CIFAR 100 kind of all the benchmark for this robust prediction. The same conclusion holds that we can achieve the best trade-off between the accuracy and also calibration error. So furthermore, we can use this estimated uncertainty to do OOD detection, right? So the way we do that is the following. So we compute the Bayesian predictive distribution using various Bayesian neural net methods, including us. And then we compute the entropy for this predictive distribution. And then we do this thresholding as to produce this label of whether it is out of distribution or not. So we use the area under the curve as the metric where we also evaluate this ROC curve and also, the precision recall curve. So you already predict that my statement here is going to be the same, right? So our approach achieves the best OOD detection performance when compared with various baselines for those inference in weight space. Okay, so just to take away, right, from this work, essentially we have shown that if you use a generalized version of attention, which is kernel attention, then you already have the mean estimate for the sparse GP. Then in order to quantify uncertainty, our recipe is to just add in the covariance part, but also we've done some work to ensure that this covariance part is not sort of like added with a super high cost. So our approach, named SGPA or SGP attention, okay, achieve basically improved calibration results while still maintaining competitive predictive accuracy. And we can use this estimated uncertainty to perform related tasks, for example, like distribution shift detection. Okay, so I've talked about how GP ideas can benefit neural networks in this transformer example. So I'm going to switch gears to the second part, which says how you can actually use these latest neural network ideas to improve Gaussian processes. And this is actually a pretty fresh work out from our lab, where we actually apply this idea called HIPPO that I will explain later to improve sparse Gaussian process. And just to mention that HIPPO is the predecessor of some interesting neural network architecture called S4 and Mamba. Okay, so this work is done again, by my PhD student Wenlong, but also my other PhD student Naoki and also Harrison. Okay, so I'm going to tell you what HIPPO is. Okay, so before that, we need to think about how to construct memory for functions. Okay, so a function defined, let's say, on a real line or in a real interval is actually an infinite dimensional object. Okay, we cannot very efficiently represent infinite dimensional objects in the computer because we need to somehow make a finite dimensional representation of it. Okay, so one way that you can build a finite dimensional representation of an infinite dimensional object is to project your function to a finite number of basis functions. Okay, so this is what we are going to do. So in particular, we are interested in this thing called Legendre polynomial, where you can look at the figure here to see roughly how it feels like. Okay, so we are going to use a finite number of Legendre polynomials and then project your function object onto this basis. So then you will get these coefficients u, and you can think about this u as a compressed or lossy compressed memory of this function, right? Because you can then use these u coefficients to get a reconstruction of your function by combining your basis function using this coefficient weighting, okay? So this is what I meant by memorizing a function via projection to a finite basis. I hope this is clear. Now we can carry on to the HIPPO idea. So previously, right, I've shown you this function defined in the interval of -1 and 1 because Lagrangian polynomial is defined in that way. Okay, but now think about actually memorizing a function defined within the interval of 0 to t. Okay, I mean, we can construct this thing called rescaled Lagrangian polynomial, right, by shifting and then rescaling this input interval of this basis function. That is not a problem. And we can also carry on with the idea of compressing this function object to a finite dimensional vector. But now the interesting thing here is that the projection, this u coefficient, now becomes a function of the time t. Okay, because our function object fx lies in the interval of 0 and t. Okay. Then let's think about an online setting where you start to observe these function values through time. So that basically means your t will grow over time. So this means if we can actually adjust this rescale Lagrangian polynomial also during time, then we can also perform this projection again, right? And then now u really becomes a function of t. Okay. So this means if we can actually figure out a way to efficiently compute the evolution of these coefficients u over time, then essentially we have a online memory of the function values that you're going to collect over time. So this is the key idea of this HIPPO project presented in this nearest 2020 paper by Albert Gu and other colleagues. Specifically, the way to derive these updates is the following, right? So think about currently at this time, you only observe the function value up to time t, okay? And then you can project your function values up to time t to your current basis to get this ut coefficient. Now, after a few more time steps, let's say delta t, right, you get new observations for f, right? So since now you want to remember the new function values, you need to also adjust your coefficient again. Sorry, adjust your basis function again, and then this will also lead to the adjustment of your coefficients. And in fact, if you actually make this delta t, very, very small, then you can actually quantify what is the instantaneous change, or like this infinitesimal change of this ut coefficient updates, which is actually written in a form of linear ODE. Okay, so the detail of this form is not very interesting. You just believe in me that you can derive these A and B matrices using the properties of the basis function. But the important thing here is that this is actually a linear ODE for the coefficients u. Okay, and when you discretize it, then it actually becomes a linear RNN. Okay, some of you might have seen this linear RNN thing in the contemporary RNN-based language models. So this also says you can use this coefficient u as a summary of the function up to time t, and you can update this coefficient ut in an online manner. So here's a summary of the idea for this HIPPO idea, okay, and the later on development. So you specify a polynomial basis, let's say Lagrange basis or like Fourier basis, right? And then you need to actually think about how you adjust your polynomial basis through time by stretching it to cover the input range of the function that you have observed right now. Okay, this will induce a function over u, that is your coefficient that depends on t, and you can actually write down the instantaneous change for this ut coefficient, which results in a linear ODE. So these ideas are actually very nice, right? But let's come back to our GP world. Okay, so one thing that I haven't told you before is that when people apply these HIPPO and the more advanced S4 member ideas to deep learning, right, their F function is actually their observed data sequence, okay, which means F is deterministic. Now, if we want to apply this to the GP world, right, remember then GPs defines distributions over functions. Okay, so now it means that instead of remembering deterministic f functions, we are now projecting stochastic or random f functions onto these basis functions. So in other words, instead of having this deterministic u, we are now going to have a random u, and we are interested in the distribution over u. But fortunately, right, this projection is actually a linear operator on the function f. And the nice thing about GPs is that if you have a linear operation over these, GP functions, then the resulting random variable is also going to be distributed in a Gaussian way. Okay, so we actually know how to compute PU. Okay, so in fact, this is actually a instance of so-called interdomain Gaussian process idea that I'm going to explain now. Okay, so this is just a refresher of the previous Sparse GP 101 slide, just to show you where we are. And the key point here is that we are going to have inducing variables U, right, to assist the scalable inference. In the previous case, these inducing variables live in the same space as Y because Z they are viewed as pseudo inputs, and Z lies in the same space as X. Now, in the interdomain inducing point variable case, U becomes different. So instead of lying in the same space as the output Y, U now is actually like these operators, a transformation of the function F. And in this case, we do this integral transformation. So it also means that there are no longer, this optimization procedure for Z anymore because there is no definition of this inducing input Z. But the important thing is the following. So the GP equations in terms of computing the posterior updates and also marginalizing out these U variables, they all keep the same. The cost for these kernel operations, right, they are still nm squared plus n cubed. They are all the same as the previous inducing input method, okay? But the major difference is in how you actually compute the kernel matrices KFU and KUU. Okay, so let me tell you how we actually compute KFU and KUU. Okay, so remember that we are going to apply this interesting HIPPO projection of the function onto this polynomial basis. Okay, right? So now F becomes random. This also means that U becomes random, and we are interested in computing the covariance between F and U. So via some interesting algebra and also pushing, this expectation inside, we can actually show that the entries to this KFU matrix becomes the HIPPO projection of the original kernel matrix in X space. Okay, since I already told you, right, that when you evolve this thing during time, you can actually use a ODE to do that. We have actually derived the corresponding ODE updates for the elements in your KFU matrix that looks pretty much similar like the previous case. So these can definitely be computed, in a similar way as the previous cases. So this is KFU. So while KUU is actually more involved because you have double integral over this f function, and each of them requires projection onto the HIPPO polynomial basis. Okay, so the derivations is actually more involved, but at the end of the day, there is also another corresponding ODE. I mean, that looks a little bit different, but it is still a ODE. If you want to solve it, you can still solve it with, let's say, simple Euler methods or some advanced numerical solvers. Another way to actually address this problem or compute the covariance matrix, KUU, is to actually do this random Fourier feature approximation to the kernels, and then you evolve the random basis functions. Okay. So we've talked about how you actually compute KFU and KUU, and once you've got that, you can just plug in that to the GP equation. So all things keep the same in that place. So one big motivation for us to do this is to perform online updates for the GP posterior. And in particular, we assume that data comes in an online fashion. For example, you observe this mini batch xt1, y1, yt1 first, and then you observe another mini batch xt2 and yt2. Okay, so importantly, you cannot revisit the previous historical batches. So this is the true online or continual learning setting. So the online GP idea, okay, from the previous was says, if you already have the approximate posterior for the previous run, then you can optimize the following online elbow to obtain the update for your inducing variable posterior distributions. So here, just one thing to say here is that you can see there are two KL terms, right? So the first KL term is just trying to address the gap of the Q distributions for the first set of inducing points when you see the second set of data points. Okay, so As I told you, right, all these kind of matrix inversion, Q distribution calculation, these equations are all the same. The change in our case is just how you compute the KFU and KU matrix. For a comparison, the inducing point-based methods needs to optimize this inducing input Z, okay, to actually update these kernel matrices. But for us, if you assume you already have the kernel hyperparameters ready, then you just compute ODE evolution. Okay, there is no optimization happening here. Okay, so just to show you the intuition about what's happening with these online updates. So here I'm visualizing you basically, some interesting figures in a 1D regression setting. So panel A basically shows you this, polynomial basis, right? And from time t1 to time t2, you obviously see this change of the basis. So this will also result in the change of the projected coefficient U. And in panel B, I'm showing you the distribution or the marginal distribution of these U variables. So you see some interesting smooth updates of this QU distribution over time, but then you also see this discrete jump because at the second time step, when I introduce new data coming from these red dots, the GP, online GP updating equation will also come in. So this will also result in the change for the version parameters and therefore the change for these coefficient distributions. Now we can use this QU distribution to show how to get these predictions. Okay, so obviously you can apply or plug in this QU distribution back to the usual SVGP framework. Then this is shown in panel D. But also you can think about here now U as this finite kind of dimension projection coefficient, right? You can use You can use this HIPPO basis function as the basis function in a Bayesian linear regression setting, and then use your QU distribution to compute this functional posterior, and this is shown in panel E. If you use enough number of these polynomial projections, then actually this panel E solution will actually get closer and closer to panel D and C. Okay, let me show you some experiment, right? So the first experiment is just a pictorial example, right? So this is a classical Gaussian process regression data set called solar irradiance. And in this case, we construct an online learning setup where we split the data set into 10 sequential tasks according to its X dimension input. Okay, you cannot revisit the past tasks once you've observed them. So here's the result, right? So what you can see here is that if you actually use the same number of inducing points, or let's say the same number of inducing functions, you can pretty much see that the inducing input-based approach, which is online SGPR, does not perform very well in terms of forgetting the old task when progressing towards the newer task. But the our approach, SGPR, actually works pretty well even after the task 10. And we can actually confirm that when you use enough number of basis function, the results will get close to online GP regression. So, and also here, just to show you in terms of runtime, right? So we compare our approach in this online setup with, let's say, inducing input-based approach, as well as another inter-domain inducing point method called, online versional Fourier features. So an immediate notice here is that the runtime for us and also OVFF is significantly faster than the inducing input-based approach. The key reason is that we don't need to optimize inducing inputs because we just evolve the basis function. Okay, so you may wonder how OVFF, these inducing point methods, perform in these prediction capability. Then I will show you later. Okay, So one interesting question that you may ask is, okay, the previous result is based on 1D basis function, okay? And my previous result in terms of online GP regression is also like 1D example, right? I also want to apply GPs to high dimensional inputs, which means X is no longer 1D, and your kernel is defined on multi-dimensional inputs. Unfortunately, there is no sort of like very efficient, multi-dimensional HIPPO polynomial basis unless you do this outer product of them. Okay, so that is not very efficient. So instead, we need to actually find a way to construct, some interesting, kernel over the time points in order to carry on for this method. So we take inspirations from, ideas of Mamba, okay, these linear RNNs in language model world, and do the following. We need to sort the multi-dimensional inputs. Okay, so here's the idea. If you can actually sort the input X to define X as a function over T, so X equals xt, then implicitly you are also defining a kernel over the time points by constructing small ktt prime equals to big K of xt and xt prime. Okay, and then once you've got this kernel over the time point, you can carry on our previous recipe. So in the Mamba world, this actually corresponds to people, cutting and tokenizing the inputs into a sequence of, let's say, tokens, right? So when people apply Mamba to, let's say, vision problems, what they do is they split the image into patches, and they are going to sort the patches in this sort of like raster scanning ordering to actually construct a sequence. And by constructing this sequence, you actually have a explicit definition of X as a function of time t, and you can carry on with their formulation. So we also do the same. So one interesting question could be actually whether the sorting method, right, has impact on the result. So here we construct a continuous learning task over some UCI regression data set. They are multidimensional, where we construct the task based on two different methods. One is to sort the input according to its first dimension. Another is to sort the input according to the L2 distance to the origin. Okay, so this is the way we actually construct the ground truth sequence for the continuous learning task. We test out our method together with some other input domain inducing point method, right, to see whether we can maintain the performance. I mean, obviously, the result is yes. Otherwise, we won't present the result to you. But the interesting point here is that whether you are using the same sorting method in the our OS-SVG framework, to the ground truth sorting will actually make some differences. So our overall conclusion is that using the ground truth sorting ordering, which we assume we know, instead of sorting according to distance defined by your kernel, actually will give you better performance. But if you actually don't know the ground truth ordering, kernel distance sort actually gives you okay-ish result. So finally, we also apply these things to even higher dimensional data via this thing called Gaussian process VAE. So Gaussian process VAE is a generative model modeling this high dimensional sequence where they use these autoencoders, right, to transform the high dimensional inputs, for example, like images or frames in videos, to a low dimensional latent representation. And then we are going to model the latent dynamics for these z variables using Gaussian process priors and posteriors. Okay, so the details are not important, but essentially in the GPVAE world, people also need to figure out how to update the GP priors in the latent space to GP posteriors in the latent space, given the observations. So we also construct a continuous learning setup on the climate dataset, a draw from era 5. So this is a dataset of 17 dimensions and also thousands of time steps. So we split the dataset into 10 tasks according to the timestamps. So each task has around 180 time steps. So we perform continuous learning on GPVAEs or various different versions of the GPVAEs by running these online SVGP methods or our methods for the latent GP update, and also this EWC method. I think it's called elastic weight consolidation method for the maintenance of the encoder and decoder. So the result here is actually quite obvious, right? That our approach maintains the continuous learning performance much better than other inducing input-based approach. So here's the takeaway from the HIPPO-SVGP. So we extend basically this idea, HIPPO, which is a predecessor of these modern linear RNNs, to the idea of improving online sparse GPs, right? So this definitely shows you that some interesting state-of-the-art deep learning methods can also benefit GP research. So our results on various kind of online GP regression and generative modeling tasks actually show that being able to maintain a long-term memory, okay, for your approximation actually helps a lot in online setting. So I want to conclude by saying some kind of interesting future direction. So obviously you can keep scaling up the approach, but then this approach needs to address the problem of reducing the complexity number and also integrate the GP computations into some GPU friendly implementations. Okay, another interesting point here is that actually deep learning people, they don't like matrix inversions because matrix inversion has a cubic cost, but more importantly, you need quite high precision compute to actually make it work. So nowadays, language models run in test time with low precision compute. So interesting question here is whether we can actually develop a matrix inversion free version of our approach. Another interesting point here is that in the use of language models, what people really care is actually the uncertainty estimation based on the input context provided by the users, right? So instead of thinking about the uncertainty quantified on the entire training data set, on the fine-tuning data set, we care more about directly answering the question with uncertainty drawn from the information provided in context. Yeah, so this drives the second line of work that we are currently doing. And in fact, we have submitted some work that actually tells you how to actually perform approximate Bayesian predictive inference for the in-context learning via some smart prompting techniques. So there's no training. This is purely by prompting. If you're interested, you can reach out to me and then I can let you know more. Okay, so this ends my talk, right? So basically, I talk about how GPs can be used to the deep learning world, and also how state-of-the-art deep learning techniques can help the GP research. So thank you for your attention. I would say that this research works would be impossible without my great PhD students.
So I'd like to conclude this by just thanking Yingzhen for today's talk. And we will now move to the question, answer, and discussion period. And the way that this will work is that we will have a period of questions that will be live streamed to YouTube. And then after that, we will conclude the live stream. And this allows those that prefer not to be broadcast to YouTube to also answer their questions. So now at this point, you can use the chat feature of Zoom to ask any questions. And yeah, let's move into that phase.
So should I read the chat, or are you going to read out the questions?
Yingzhen, you should read the questions from the chat because so that way people on YouTube know what the questions are.
Okay, then I should open the chat. Okay. Okay, the interesting question is why do SVGP fit well when used in multi-layers of a transformer model, even through stacking GPs? Okay, that is an interesting question. Okay, so first, from the GP of deep GP world, people actually observe that at least in terms of the mean fits, it seems okay. The uncertainty behavior can be a bit weird. Okay, but I would refer you to basically deep GP researchers to talk more about the uncertainty behavior. Back to our work, right? We really pretty much leverage the power of transformers because really our mean implementation is really just a transformer, except that we replace the softmax attention to kernel attention. So this basically says whatever interesting, engineering techniques that people have tried to make transformer work, we can benefit from that. Okay, so the next question here is okay. So the question here is how these kind of tools can lead to practical consequences today. Okay, so that is an interesting question. So in terms of the sparse Gaussian process attention work, right? So obviously people no longer do massive pre-training, at least within academia. But when you're going to use the pre-trained transformers for, let's say, fine-tuning, right? Then you can actually, during the fine-tuning, add in the Bayesian touch. You can do that either via, let's say, the weight space view, which is this version LoRa approach pursued by others, or you can also do our approach, which is adding in the covariance part. You can still keep the mean and intact. So the other side, right, in terms of Gaussian process, right? So we are actually now in discussion about, extending this second Gaussian process work into more interesting application scenarios like disease modeling and some climate modeling case. Our hypothesis here is that, in those domains, GPs are actually very useful. We want to make it even more useful and better performing by introducing neural network-based techniques. Okay, so the open-ended and speculative question, what do you think the long-term implication of research connecting GPs with deep neural networks will be? Okay, what would be the big things of community to remember from works? Okay, so interesting. So I would probably say two things. So one, the reason why, I haven't been doing a lot of GP works until now, given that I did my PhD in a lab that work a lot of GPs, is that I usually think about GPs in a way to somehow consolidate my thoughts of research. So I use that as a thinking tool, but I still want to do deep neural networks as the practical thing. So one thing I would say here is that developing GP-related intuition for deep neural networks can be very useful in terms of understanding the behavior of deep neural networks and think about what kind of uncertainty behavior you want. I mean, again, I still hope that one day, the representation power of GPs and related related line of work like deep GPs, can be improved further so that we really get this, very flexible class of probabilistic models, but with, principled uncertainty quantification methods.
Okay. Thank you so much, Yingzhen. And I'd like to take this opportunity to conclude the YouTube live stream and move on to the second phase of question answering. And before I conclude, I wanted to thank all of our listeners on YouTube for joining us today and remind everybody that we have another seminar coming up next week. Actually, we have two more for the season. So check out the schedule on our website, which, to remind everybody, is gp-seminar-series.github.io. And please feel free to sign